All right, let's talk about the invisible rule book that keeps some of the biggest ships on the planet from becoming floating catastrophes. It's called the IGF code, and it's all about how to keep gas-powered megaships from, well, going boom.
So, picture this. You've got a ship that's literally bigger than a skyscraper, and it's powered by a fuel so volatile it has to be kept at temperatures colder than deep space. Now, what happens if that ship gets caught in a hurricane? Or worse, has a collision? How do you make sure it's an engineering marvel and not just a ticking time bomb? That's the huge puzzle the entire shipping world had to solve.
You know, everyone wants cleaner energy, and that goes for the high seas too. Natural gas is way better for the environment than old-school ship fuel, but here's the catch. It is way, way more flammable. So you're stuck with this massive balancing act between doing the right thing for the planet and managing some really serious safety risks for our oceans and ports.
So how in the world do you handle a risk that big on a global scale? Well, you definitely don't leave it up to individual companies to figure it out. No, you create one universal set of rules that every single ship in every single country has to play by.
Yeah, this wasn't a problem one company could just fix on its own. The International Maritime Organization, you'll hear it called the IMO, got the best naval architects and engineers from all over the world in a room together. Their job? Create a single, mandatory global standard for these new gas-powered ships. And what they came up with is the IGF code.
The code was adopted back in 2015, and it's been the law of the sea since 2017. And we're not talking about a list of polite suggestions either. This is serious maritime law. Now, to really get why it's so important, we got to get on the same page with a few key terms.
Okay, first up, low flashpoint fuel. The easiest way to think about it is like this. Traditional ship fuel is kind of like a big log in a fireplace. You know, it takes a lot of effort and heat to get it to catch fire. Natural gas, that's more like a cloud of gasoline vapor. One tiny spark is all it takes. And that one difference changes literally everything about how you have to build a ship.
Next, you've got bunkering. That's just the sailor's term for refueling. But with natural gas, it's not like pulling your car up to the pump. Oh no. It is a super high-stakes, carefully choreographed dance of moving a freezing cold, explosive liquid from one place to another. The IGF code has a whole chapter just to make sure that process doesn't end in a complete disaster.
And finally, hazardous area. The code makes designers map out every single part of the ship where a gas leak could happen and create an explosive mix of air and fuel. And in those zones, every single piece of equipment, and I mean everything, from a light bulb to a simple fan, has to be specially designed and certified to be completely spark-proof.
Okay, so now that we've got the lingo down, let's see how these rules actually get built into the steel of a ship. We're going to start in the engine room, where you'll find two totally different ideas about what safety really means.
The big question for any designer is this: what's your plan for a gas leak in the engine room? Do you build an impenetrable fortress to make sure it can never happen? Or do you build a super-sensitive alarm system that can react in an instant? The IGF code actually says, hey, both are valid options.
So on one side, you have the gas-safe approach. Think of it like a Russian nesting doll of safety. Every pipe carrying fuel is inside another, bigger pipe, which creates this double-walled, totally gas-tight barrier. It's basically a bank vault. Then you have the ESD-protected philosophy. This is more like a high-tech museum. The room is rigged with sensors, and the very instant a gas leak is detected, an emergency shutdown, or ESD, is triggered. It cuts the gas supply and kills every possible source of a spark. It's all about neutralizing the threat before it even has a chance to start.
Picking a strategy for the engine room, that's a huge decision. But honestly, it's only half the battle. The real challenge, the one that probably keeps naval architects up at night, is figuring out how to safely store thousands of tons of this super cold fuel for months at a time.
And that brings us to the heart of the ship, the fuel containment system. We're not talking about simple metal boxes here, we're talking about massive, multi-layered, high-tech thermos bottles. And trust me, the IGF code is painfully specific about every single detail of how they're built and where they go.
To protect against a collision, the code basically says you have to bury the fuel tanks deep inside the ship's hull, almost like a jewel inside a steel box. The rules are super precise. The tanks have to be pushed in from the sides by at least a fifth of the ship's width and lifted up from the bottom by at least a 15th. It's all about creating this big, shock-absorbing buffer zone all around the fuel. But look, even the best buffer zone in the world won't help you if the tank itself fails.
And that's why the IGF code doesn't just have one type of tank. It gives you a whole menu of options, and each one has its own clever way of dealing with a potential cryogenic disaster. As you can see right here, the options are pretty different. You've got the super cautious membrane and Type A tanks, which are basically a tank inside another tank. Then you have the more high-tech Type B, which uses some really advanced engineering to get away with just a partial backup barrier. And finally, you've got the tough guys of the group, the Type C tanks. They are so ridiculously over-engineered and strong that they don't need a backup barrier at all.
So what's the big deal with this secondary barrier anyway? Well, it does two critical jobs. First, it's your absolute last line of defense to contain a leak. But just as important, it keeps the ship's actual steel hull from ever touching that cryogenic fuel. Because at minus 162 degrees Celsius, that liquid would make the steel hull shatter just like a pane of glass.
And hey, if you thought we were getting into the technical weeds before, just look at this. This table is pulled straight out of the IGF code, and it tells engineers the exact safety factors they have to use for different kinds of steel in one of those Type B tanks. I mean, this is the level of obsessive detail we're talking about. The code doesn't just tell you where to go, it gives you a step-by-step, painstakingly detailed map to get there safely.
Okay, so after all that, after this deep dive into the nitty-gritty of ship design, what's the big takeaway? Why should a rulebook for a few super specialized ships matter to the rest of us?
Well, you don't have to take my word for it. The code's own introduction, its preamble, sums it up perfectly. The goal is simple, but it's also profound: to minimize risk. The code looks at the real dangers of these new fuels and just provides a clear, engineered plan to keep the ships, their crews, and our planet safe.
When you boil it all down, the IGF code is so much more than a rulebook. It's the key that makes a greener future for global shipping even possible. It gives everyone a common language and a shared set of safety rules so the industry can switch to cleaner fuels without gambling with our safety.
But the story doesn't end here. The IGF code was a brilliant answer for the natural gas problem. But now, the shipping industry is already looking at the next generation of fuels, things like hydrogen and ammonia, which are even more challenging. So a new, even smarter rulebook is going to be needed. The big question is, what will that rulebook look like, and what incredible new ideas will engineers come up with to keep us all safe on the next leg of our clean energy journey?